Good evening, everyone. Welcome to the February meeting of the Madison Astronomical Society. While I have everyone's attention, let me know if you have not had a chance to sign our attendance list. Since it's I'll pass it around. Just pass it around to anyone who hasn't had a chance to sign it yet, both for members and guests. Thank you very much. Before we go to our feature presentation tonight, I have a few announcements to share. First of all, there's a lot of interesting, besides the presentation, the very fascinating presentation we have for you tonight, there are some, coming up in this next week, there are some other things. If you're into learning more about astronomy and the history of astronomy, there's a lot going on. On Sunday, February 11th, at the lecture hall at the Madison Museum of Contemporary Art, that's on 227 State Street. Again, that's the lecture hall at the Madison Museum of Contemporary Art. There is a presentation titled Chasing the Stars, Women Computers at the Washburn Observatory. And that's being presented by the Director of Space Place, Dr. Jim Lattice, and also being presented by Kelly Terrell. And I'll tell you what it's about. In honor of the International Women in STEM Day, James Lattice and Kelly Terrell will give a presentation about the early days of astronomy studies in Wisconsin, emphasizing the role of female astronomers and their contributions to astronomic research. So that's Sunday, February 11th at 2 p.m. Sounds fascinating. Especially if you've seen, what was it, the redo of Cosmos, I think, and there's been other documentaries on television about women computers. They called them computers that contributed a lot to early study of stars, categorizing stars, or even if you were one of the famous computers at NASA. For the first very few space missions, like in one of the movies that came out a few years ago. It's a very fascinating subject. Also, coming up on Tuesday, February the 13th, right here again at Space Place, there will be a presentation at 7 o'clock called A Stellar Mosaic, Piecing Together the Lives of Stars by Evan Lennick of the UW-Madison Astronomy Department. And the synopsis is, individual stars can live for billions of years, meaning we humans can only see them for very brief moments of their lives. This talk will explore how we construct models of stellar evolution from these snapshots and how these models inform our understanding of stars that deviate from normal stellar evolution. Again, that's right here at Space Place, Tuesday, February 13th at 7 o'clock. Our next month's meeting will be on Friday, March the 8th, and we will be having a presentation by two of our club members, Bob Hamers and Jeff Schockler, and their presentation is called Prepare to be Gobsmacked, the April 2024 Total Solar Eclipse. So if you're interested in learning how to view the eclipse, either locally or traveling, I think they're going to be encouraging you to travel if you can, because you will be gobsmacked if you go to the path of totality, and not so much if you stay around and just see the partial. I think back in 2017, I knew, like animals and stuff have like panic attacks and freak out when there's a total solar eclipse. So when totality happened and I started having a panic attack, I knew I needed to start breathing, and it was really thrilling. So do prepare to be gobsmacked. That's coming up here again at Space Place on Friday, March 8th at 7 o'clock. Now, I don't see every month the Madison Metropolitan School District Planetarium at Memorial High School usually has monthly presentations, and I noticed that their next presentation isn't coming up until the week of March 19th. So on the March 19th and Thursday, that's Tuesday, March 19th, and Thursday, March 21st at 6 and 7:30 p.m., they're going to have a ticketed event called Living in Balance, Join us for a planetarium experience exploring the full dome video production Living in Balance, Anishinaabe Star Knowledge, that highlights Anishinaabe stories of constellations and moon in relation to contemporary insights about environmental changes. Teaching shared by the native skywatchers Carl Galboy, William Wilson, and Dr. Annette S. Lee are narrated by Aaron Dokum, with Ashkenazi one translations by Alphonse Pakanawat, I don't know if I'm saying that right, set to art by Elizabeth Lepenzi. I don't have Mike Lecrone's. If you're familiar, a longtime resident with Mike Lecrone, he had this knack for being able to pronounce people's names correctly. I don't have that ability. So, and they also, as usual, if you go to these planetarium presentations every month, they'll also cover certain things going on in the skies that month. So it's a lot of fun to go see. It's a very high-end, very modern planetarium setup there. So I encourage everyone to go there. And again, that's going to be on the week of March 19th, on Tuesday, March 19th, and Thursday, March 21st, with ticketed shows at 6 p.m. and 7:30 p.m. And for Madison residents, it costs $6 per person, and non-residents, $9 per person. And those tickets can be purchased online. And then if you show up there and they have tickets left, it'll be cash only. Any questions on any of the announcements so far? I also anticipate, depending on how the weather shapes up, next month we may be resuming our monthly scheduled, once a month planned star parties at Yana Research Station. For those of us who might be newer to the club, Yana Research Station is our observatory site in Greene County, in northern Greene County, just south of Brooklyn and further south of Oregon. And once a month we like to have, a set date where there won't be much of a moon, and hopefully the observing will be really good. And now that the observing site is kind of upgraded, it'd be great to get everybody back down there and do some observing. So we'll be doing this throughout this year on a monthly basis, especially if there's a new moon coming up. Or we may even decide, hey, this will be a great, maybe this month we'll do some solar observing or something like that. So we're always open up to ideas. So stay tuned with regard to that. With all the rain and thawing and muddiness lately, if you do go out to Yana Research Station, please be aware that the ground could be very soft. So we encourage people to park their vehicles in the areas south of the line of arborvitae bushes and trees. Because sometimes if you park in the grassy areas around the observing site, it's possible to get your vehicle to kind of get spinning in the mud, and you can get seriously stuck, and then the next thing you know, you're struggling with cellular service trying to call a tow truck. So be extra mindful about the muddiness out there. Any questions about Yana Research Station? And if you're interested, usually when it just turns out tomorrow night it's looking really clear, it's hard to tell far in advance if it's going to be a good time to observe. So in a day's notice, a bunch of us might get on our observers list, what we call the YRS observers list, on our Google account. And if you contact Jürgen and let him know, hey, I want to be put on this MAS observers list, you will get a heads up when people are planning to go out to Yana Research Station and observe. So let Jürgen, the fellow sitting in the middle with the green sweater, that's our secretary, let him know if you'd like to join that. Email us, the treasurer. Sorry, treasurer. Thank you. All right. It looks like we have about 5 minutes before our presentation begins. Oh, yes, Jürgen.
Yeah, I did want to make one comment. Microphone, right?
Yep. Oh, thanks for reminding me.
Those of you who may have seen me walking up here and putting things in the back room, we have some hoodies, the MAS hoodies. We have an order of them. We have two back there that are the different sizes. We actually have 5 different sizes, and we'll have, when 3 of them reappear, we'll have demos that you can try on. We also had a new order for caps in. That's what I was carrying back and forth. They're blue with the MAS logo, and there's white with the MAS logo. Those are $10 each. The hoodies are 35 or 40, depending on what size you get. The extra large are 40. So if you're interested in those, you can see me after our presentation today. I'll hang around for a short while, and if anybody's interested, we can talk about them then.
And we also do have coffee mugs too. So
How much are we charging?
I think it's like $10 off. I forget. Yeah, don't take my word on it. I have somewhere on my smartphone. I do have a memo that reminds me what the price is for everything. So don't quote me for sure. But when I look at that memo, then you can. So. Hey, there might be some newer faces here. Is there anybody here who has never visited us at Madison Astronomical Society before that would like to introduce themselves? I'll just start going around. You don't want to introduce yourself? Yeah,
Hi, I'm here because Jessie's my best friend, but it's exciting to be here. My name is Morgan.
It's nice to meet you, Morgan. Great to see you. Next, yes.
Hi, Will Cox. I'm new here and a novice, just wanting to learn, so I figured this would be a good place to kind of learn from the experts.
Great idea, because there's a lot of enthusiasm. Oh, yes, Jürgen? Oh, you're a new member then. So are you a regular or observing member? Regular. But yeah, like I was saying about the monthly star parties, keep the monthly announcements you should receive. All members should receive a monthly announcement when it comes out, like a week before the monthly meeting. And in there we'll have dates and times for the monthly star parties. And when you head to one of those star parties, if we got good weather, it'll be a perfect opportunity to see all the different kinds of telescopes and binoculars and other gizmos that people like observing with, and get an idea of what's right for you. So, what was your name again? I'm sorry.
Will Cox.
Will Cox. Nice to meet you, Will. I'll be right with you. Yes, sir. What's your name? Nice to meet you.
My name is Jonathan Troville. I'm an imaging physics resident here at UW, and I work with Frank Rinaldo here. And for a while, I studied astronomy as an undergrad, so I'm just excited to learn new physics.
It's great to meet you. That's great studies. Thank you for studying physics. The math was just too much for me, so I went for chemistry instead. Have I gotten to everyone who'd like to introduce themselves? Well, great. We're almost ready to begin our presentation, and I'd just like to encourage everyone, especially those of us who have been here in the past, who have had other updates on the ongoing research at IceCube, feel free to raise your hand and ask a question, and our guest speaker will get to you when she can, and she may also stop during some of her parts of her presentation for questions. So hang on to those questions, and she'll be more than happy to respond to you. Before we move on, is there any more questions? Oh, yes, Chris?
No questions, but I just wanted to mention, it's been out there for a while. I believe it's on Amazon, a movie called A Million Miles Away, about a Mexican young man who came up to the U.S. to became an astronaut. Phenomenal movie, and it left me with such a good feel for what it really takes to become an astronaut. It's god-awful hard.
What was that name of that movie again?
A Million Miles Away.
A Million Miles Away.
And I believe it's Amazon.
Amazon. Thanks so much for sharing that, and especially if anybody has ever seen an obscure movie that they'd like to share with us, or if you have an recent observing experience that you would like to share quickly too, feel free to raise your hand. Saturday night was phenomenal. That's what we hear. Okay. All right. And yes. Sorry to lug this microphone around.
Hey, Michael. I was just going to plug the Southeast Wisconsin Astro Imaging Group. They usually meet the second Wednesday of the month, so they usually meet right before us. But this month, they're meeting the 14th, which is after us. So they meet 7 to 8:30 p.m. The meeting this month is on Do Luminance Subs Improve Modern RGB Imaging Results? So a little bit of a controversial topic for imagers, but
yeah, especially as techniques and technology become more advanced.
Yes.
Sometimes people might cling on to the old methods, even though that maybe the
No,
old
they don't
methods.
Yeah, so this one is on Zoom. They usually do it on Google Meet. I think to get the information, they can email you, and then you connect them to the Milwaukee group, or?
They can always email me information, especially if it's like a Zoom link. And I have instructions like, of who I should share the Zoom link with, because sometimes, you don't want someone to just kind of barge in who isn't part of the group and disrupt the meeting, so. Yeah, and especially for people, because I know all the time we get newer members that are interested, kind of curious about astroimaging. And we are, some of our avid astroimagers are meeting with the avid astroimagers from the Milwaukee area into this combined group. So it's just going to be a great forum for anyone to kind of learn about the topic and ask questions, especially if you're having trouble with a particular thing. All right. Well, it looks like it's 7:31, and we shall get on with our guest presentation tonight. This month's presentation is entitled Chasing Ghost Particles, presented by Jessie Thwaites. And I'll just tell you a little bit about it. Neutrinos are tiny, nearly massless particles that interact very rarely. Because of this, astrophysical neutrinos can travel very far, all the way to the South Pole, carrying information directly from their sources. The IceCube Neutrino Observatory, which UW-Madison has had a lot of put in a lot of effort to really set up this observatory. So this is really a hardcore UW-Madison, really neat thing. The IceCube Neutrino Observatory has detected these astrophysical neutrinos, but only a few sources have been identified thus far. We search for these neutrinos from transient sources that vary on the brightness over time, such as gamma ray bursts, supernova, nova, mergers of compact objects. These sources often have very energetic processes happening inside them to accelerate particles to produce these neutrinos. So this is very interesting physics. And just to tell you a little bit about Jessie Thwaites is a 4-year graduate student at UW-Madison's physics department, working with Justin Vandenbroek at the IceCube Neutrino Observatory there at the South Pole. Their research focuses on searching for high-energy astrophysical sources of neutrinos from transient sources in both real-time and archival data. In addition to research, Jessie writes for Astrobytes, a daily science communication blog that summarizes astronomy or astrophysics papers into bite-sized pieces for the public. Outside of physics, Jessie plays horn and enjoys hanging out with her cat, Ryan. And what horn do you play? French horn, great. Yeah, it's too bad John Wonderland's another French horn player that visits us, but to me, being kind of a jazz musician type fan, a horn can mean saxophone, can mean anything that you play that way. So it's my pleasure, everyone, to introduce you to Jessie. Thank you for being here.
Okay. Oh, yep. That works. Okay. Sorry, that's a little loud, I think. Yeah, so thanks for the introduction. Hi, everyone. Yeah, my name is Jessie, and today I'm going to talk about my research, which is looking at the universe through a different lens than maybe we normally talk about when we consider astronomy, which is neutrinos. So I'm going to get started with an image that's probably pretty familiar to several people in this room. I'm going to kind of orient you to what you're looking at here. So basically this is similar to if you were looking at the globe, but instead of looking down, you're actually looking out. So this is the full sky, and this is the picture of what we're seeing in visible light. So across the center of this picture, right down the middle here, is our galaxy. So this is oriented so that the center of the galaxy is here in the center, and then the plane of the Milky Way is here, and you can see the large and small Magellanic Clouds there, as well as some of these darker patches, which are dust that is in our that's in our galaxy. So this is one view of the sky, but if we change wavelengths slightly and we look at it in a slightly different way, say if we go to the radio band, then we can still see that galaxy picture that I just talked about straight across the center, but now we see a slightly different image, and you see different features. So you see kind of those almost swooping features across the top there, and the galaxy looks different in this wave band. And now if we go to another different wave band, so go slightly higher in energy, we get to the microwave. And once again, you can see the galaxy right across the center, but then you also see other features that don't look the same as either the radio or the optical. And if we go to the highest energy light that we can see, the gamma rays, once again we see our galaxy, but then we also start to see these points that are actually outside the galaxy, and those are actually coming from other galaxies outside of our own. So looking at the universe in all of these different wavelengths of light is called multi-wavelength astronomy. And by doing this, you can get different information about the sources you're looking at just by looking at them in a different way. Another way that we can do that is actually by looking not just in light, but in other particles that we can see from these sources. And that's called multi-messenger astrophysics. So I've talked about one portion, so one piece of our multi-messenger puzzle, which is light or photons. There's 3 other pieces to this puzzle that I'm going to talk about now. So I'm going to start with cosmic ray physics. So in 1912, a man named Victor Hess ascended in a balloon. So this is a picture of him as he was about to go up. And he measured the amount of ionizing radiation with an electroscope as he went up. When he did this, he found that it actually increased as he rose in the balloon rather than decreasing, which he took to mean that it was coming from space. And this is the discovery of cosmic rays. So what actually are cosmic rays? These are nuclei that are coming from different cosmic accelerators in the universe. So these are charged particles. We see them from all directions with very high energies. So they can have energies as large as 10 to the 21st electron volts. So to kind of give you an idea of what that energy looks like, some people may have heard of the Large Hadron Collider, which is built underground in Switzerland and France. It is a particle accelerator, so it accelerates particles to very high energies and then actually smashes them together to do high energy particle physics and to learn more about the particle physics of those. And to get to this energy that I'm talking about with a particle accelerator the same way that we do it for the LHC, you would actually need an accelerator that has the same radius as Mercury's orbit to get to these energies. So this is extremely high energies that we're seeing from these charged particles, which are coming from different cosmic sources that are able to accelerate them all the way up to these high energies. So that brings us to our second piece of the puzzle, so cosmic rays. So now we have light and we have cosmic rays. So now I'm going to talk about another messenger, which will be a focus of this talk, which is neutrinos. So what are neutrinos? They were proposed in 1930 to conserve energy in beta decays. So when you have a neutron that is decaying to a proton and an electron, if you measure the energy of that proton and you measure the energy of that electron, and you take only those two, you don't actually see conservation of energy. So if there was no third particle, we would expect that if you measure the energy of the proton plus the energy, of the electron, then it should match the energy that you started with the neutron, and it doesn't. So this man, Wolfgang Pauli, suggested a third particle that was being produced in this that is chargeless and massless. Oops, sorry. And he proposed this particle to be chargeless and massless, and he called this a neutrino. When he proposed this particle, he actually thought that we couldn't possibly be able to detect it because it was chargeless and massless. So he said, I've done a terrible thing. I've postulated a particle that cannot be detected. Well, he was wrong, thankfully for us. And they were actually detected 26 years later in 1956. So what actually are they? Neutrinos are fundamental particles, which from a particle physics standpoint means that you can't break them down into any other components. They are the smallest piece that you can have. And they're very interconnected with cosmic rays. So they can be produced by the interaction of cosmic rays with material around cosmic accelerators. So you can have these charged particles that are accelerated to these high energies, but then they can smash into each other or into material around them, and those interactions actually produces neutrinos. So we can use neutrinos to look for these high energy cosmic ray sources. And because neutrinos are chargeless and nearly massless, they can travel very long distances without interacting, so we can actually see neutrinos that are coming from these sources that are extremely far away. And they can make it all the way to us basically in a straight line. So that's the third piece of this puzzle of multi-messenger astrophysics. There's one more piece that I want to introduce to you, and that is gravitational waves. So these were predicted by Einstein as a part of general relativity, and they are ripples in space-time. So there's a couple different ones that you'll hear about, but for this talk, I'm primarily going to focus on compact object mergers. So when I talk about a compact object, I'm talking about something that is extremely dense, a black hole, a neutron star, or a white dwarf. And when they orbit around each other in a binary, they are able to distort the space around them as they move. So in this animation, right here at the center would be, we'll say, two black holes, and as they're orbiting each other, they're creating these gravitational waves, which are these ripples that you see coming off here. And when those objects merge, we see a very characteristic signal in gravitational waves. So that completes our puzzle of multi-messenger astrophysics. So by using these four different messengers, we can look at some of these high energy cosmic accelerators out in the universe, and we can get a new picture on what's happening near them, or what's happening in some of these mergers, for example, and we can get a new window on our universe. I would like to pause here and ask if there's any questions before I move on.
You raise your hand and I'll bring the mic to you. Do we have any questions online?
Okay. That's totally fine. I will move on. So, I've told you a little bit about what neutrinos are, but how do we actually detect them? I said that they are neutral and nearly massless, and that they interact very rarely. This is a good thing for us if we're trying to do astrophysics, because those neutrinos can make it all the way to us from these sources that are so far away outside of our galaxy. But this also makes them difficult to detect. So one way that you can get around this is by building a very large detector, and that's where the IceCube Neutrino Observatory comes in. So this is a picture of IceCube. The IceCube Neutrino Observatory is at the South Pole in Antarctica. So to orient you on this picture a little bit, this hexagon, this white hexagon on the top, is actually the Antarctic ice. So the IceCube lab is in the center there. So that's actually the surface of the ice. And then our detector is actually drilled into the ice and is suspended on these strings. So this is, in total, a cubic kilometer instrumented in the ice at the South Pole. It has 86 strings, which each have 60 light sensors on them. So this is a picture of one of our light sensors. We call this a DOM, a digital optical module. And there are 60 of these per string, which brings you to a total of 5,160 DOMs that are instrumented into the ice. What we do is we drill with a hot water drill down into the ice, down, I don't know if you can read this, it's a little small, but about 2,500 meters into the ice. And then we send these strings with these light sensors attached on them. Normally this would also be a full sphere, but the top has been taken off so that you can actually see the electronics on the top there. The main array is sensitive to high energy neutrinos. So in the TeV range, so that's 10 to the 12 electron volts, this is actually about the same energies that the Large Hadron Collider that I was talking about earlier operates at. And there's also an infill array, which here is kind of highlighted in like this very light green, which is called deep core, which is able to detect lower energy neutrinos. So those are in the GeV scale, so 3 orders of magnitude lower energy. And that is made up of 8 strings which have denser instrumentation to give us the sensitivity to those lower energy neutrinos. So here is an aerial view. So this is what it actually looks like at the South Pole. You can see South Pole Station here. And then you can see a skiway where planes would come in. The IceCube lab is there in the center. And then that hexagon that I showed you on the previous slide is shown there in the black. So that's actually how large IceCube is. IceCube was completed in 2011. It took 7 seasons to drill all of the holes. So this is actually a picture of the drill team after the 7th string, or after the last string was placed. And then here you can see the string with one of the digital optical modules going down into one of the holes. So what do neutrinos actually look like in IceCube? So what happens and what we actually detect, because I said that we had these photosensors, is the neutrino comes in, interacts with nucleons in the ice to produce a charged particle, which then emits light. And it's that light that we're actually detecting with these photosensors in IceCube. So I'm going to show you an animation of a neutrino coming into the detector. It interacts, and then it produces light along its path. So you can see it interact, and then this arrow showing you the direction that it's going. The colors are showing you where it deposited light. I'll play it one more time. It's a little quick. Maybe. There. So there it interacts. And all of the colored dots are each of those light sensors that we have, and that's where the light was deposited in the different sensors. So to show you a stationary picture, so each of these dots is one of those photosensors. The size of the dot tells you how much light it saw, and then the color tells you the timing information. So red is early, blue is late. So here you can see that this neutrino came over here, interacted somewhere over here, and then went through the detector like this. So this is called a track. This is one of the more common signatures that we see in our detector. There's really 2 very common ones that we see. And this one points back to the source. So you can trace back where this neutrino came from with a pretty good degree of accuracy at the high energies, usually within about a degree. So fairly good pointing resolution for us. And then the other very common signature that we see is called a shower or a cascade. So for this case, you see the neutrino came and interacted about here, deposited a bunch of light, which then spread outward. So these are a lot more spherical. It's a lot harder to point back to a source looking at these, but they have really good energy reconstruction because they deposit all of their light inside of the detector rather than carrying some of it out like this one does. So the goal for what we're doing and what I'm going to be talking about is doing multi-messenger astrophysics. So looking for neutrinos from sources detected in other messengers. This is very challenging. There's lots of background from cosmic rays interacting in our atmosphere. So rather than waiting for a clear night that's very dark to go observe, where you can point directly at a source and you can definitely see that source, it's kind of like doing astronomy during the day. So you have a very large background that you're kind of fighting through, and we actually use statistical methods so that we can pick out sources from all of this bright background. So to kind of give you an idea, every year IceCube sees 100 billion atmospheric muons, 100,000 atmospheric neutrinos. So those 2 are coming from cosmic rays interacting in our atmosphere, and 10 astrophysical neutrinos. So we want to pick out those 10 astrophysical neutrinos from this very large background that we're seeing. And the way that we do this is using statistical methods to pick our sources out. Sorry, is that a question? Yeah.
Yeah, I had one question. The neutrino just interacts. I'm sorry. The neutrino just interacts once, right? And then,
Yes.
so the track that you're seeing is not multiple interactions of the neutrino. The neutrino is creating a charged particle in its interaction, and then it's traveling in the same direction neutrinos because conservation of momentum.
Correct.
And so what kind of particles are being produced by the neutrinos, I guess?
Yeah, that's a good question. So there are, I'm going to actually go back to that picture. So there are 3 types of neutrinos, and they each have a charged lepton that's their partner. So you're probably all familiar with electron, but then there's also a slightly heavier electron, which is a muon, and then even heavier is a tau. And we have all 3 of those in neutrinos as well. So this particular one actually came in and produced a muon, which has a longer lifetime, so that's why we see this nice track. And this one could be a couple different ones. So it could be producing an electron, it could be producing a tau, and this one could also be what we call a neutral current interaction. So that's basically like a scattering interaction, where it deposits a bunch of energy, but really just scatters and the neutrino actually goes out. Does that answer your question? Yeah. Okay, cool. Yeah.
And Jessie, we had another question from online.
Yeah.
Kevin's asking, how often is ICE detecting? Wait a minute. Yeah. How often is ICE detecting a new source for neutrinos versus a known source?
A known source being something in another messenger, or?
If you're detecting it and you're trying to detect the sources, sometimes are you getting neutrinos from sources that you expect, like the sun? The nuclear reactions generate neutrinos, so that's kind of a background, or some other known source versus an unknown source.
Right. Yeah. So yes, we definitely can be. From the sun, they're called solar neutrinos, so we definitely are. As far as other unknown sources, it's, like I said, it's hard to pick them out of the backgrounds. So we kind of need to look at known sources in light or in another messenger in order to kind of pinpoint where they might be coming from. So there could be sources that we haven't seen yet in neutrinos. I'm not sure if that answers the question very well.
I think it probably does. And one more question from John. How many of the observers for IceCube actually visit the site in Antarctica? Or is it because of the remoteness, is all the observing done remotely?
Yeah, a lot of it is done remotely. So I think most people who go to Antarctica are going there to do detector operations and do some of the operations side of things, or are going to actually drill these holes. I personally have not gone. I know a couple people at UW who have gone to the South Pole, but I think mostly for like operations kind of activities. A lot of what we do is remote. So the data actually comes from the lab in the South Pole and comes directly up north, and then we analyze the data here. So up north being, everything is north from the South Pole. Yeah. So the data comes up to Wisconsin or to any of the other institutions, or can be analyzed by anybody in the IceCube collaboration from there.
Thank you.
Yeah. Yeah, so I'm actually about to talk about sources as well, and some of the sources that we've seen. So one method for cutting down on all of this background and kind of amplifying your signal is to use a lot of data. So recently, the IceCube collaboration looked in the direction of 110 known photon sources using 10 years of IceCube data. Oh, that's really washed out. But we looked in the northern hemisphere, and we looked at a couple different possible sources. So this is just that northern hemisphere part of the sky. And we found evidence for neutrinos coming from Messier 77, which is also known as NGC 1068. So what actually is this object? This is what we call an active galactic nucleus. So this is a supermassive black hole that is actively eating material from around it. This particular one is a type of active galactic nucleus that we're actually seeing from the side. So we're kind of seeing a side view of that particular galaxy. So that's kind of what we're seeing here. So we don't actually see the black hole itself, but you kind of look at it through the side. Another way that you can do that is looking at transients. So transients are any source that's only detectable for a short time. So I put a few examples here: flares, supernovae, novae, gamma ray bursts, fast radio bursts. There are many others. But you can cut down on your background by looking at short time windows. So essentially, if you cut down the amount of time that you're looking and you look in one particular direction, if you see something from that direction, then it's more likely to be coming from your source. If we do this quickly while the event is happening, then this is called real-time astronomy. So we're not waiting to publish a paper, but we're sending it out to the community as that particular event is happening. And we do this so that we can inform other telescopes what's potentially interesting for them to follow up on with their own observations. So another source that IceCube has detected was actually detected in real time. On September 22nd, 2017, IceCube detected a high-energy neutrino and sent it out to the astrophysical community. So this is actually one that I showed you a couple slides ago. This is a track. So now the color scale's changed a little bit. So now blue is early and yellow is late. And you can see the direction that neutrino went through the IceCube detector via this arrow. So that's kind of showing you the direction. And then there's actually a top view here. So we sent that out via a public telegram to the astrophysical community, and it was followed up by a huge network of other observatories. So Swift, Magic, Fermi, many others all followed up the direction that this neutrino came from, and it was actually found to be coincident with a flaring blazar. So this particular one is TXS 0506 plus 056. And what a blazar is another one of those active galactic nuclei, so a supermassive black hole actively eating material around it, but it's actually spewing out a jet, which is particles that are accelerated to near the speed of light along its axis. And in this particular case for a blazar, we're actually seeing the jet, so that jet is actually pointed at us. So that's what we're seeing for this particular source. So now I'm going to talk about another source that is very interesting to us, which is gamma ray bursts. These are very high energy flashes of the highest energy light that we know of, which is gamma rays. They are very short, so they last a fraction of a second to on the order of minutes. And there's really two types. So we can kind of split them based off of their duration. So we have short gamma ray bursts, which are less than 2 seconds, which generally come from mergers of compact objects. So those compact objects are black holes or neutron stars. And then we have long gamma ray bursts. So those are greater than 2 seconds, and those are coming from supernovae, so deaths of stars. So I'm going to talk about both types, but I'm going to start with the long GRBs. And I'm going to start by talking about the brightest of all time, aka the BOAT GRB. On October 9th, 2022, so very recently actually, the gamma ray burst monitor on board the Fermi satellite saw an extremely bright flash of light. So this is what they saw. Here you can actually see the galaxy right here, and then the burst, which is this big flash, and then it kind of fades away. It lasted about 5.5 minutes, on the order of 300 seconds. And it actually had some of the highest energy gamma rays that we've ever seen from a GRB. So this is the first time we saw gamma rays above 10 TeV from a GRB. And we were also able to do some really cool physics with this burst. One of the things that we were able to see was actually we were able to probe the dust in our galaxy in X-rays. So as light came from this supernova, it propagated through, and because it was so close to the galaxy, it interacted with dust and was scattered, and that's these rings that you're seeing. So this is actually several days after the supernova. This is in X-rays, and you can see these rings of light which are scattered light off of dust as it's traveling towards us. So this was some of the really cool physics we were able to do with this particular GRB. So, like I said, the source of long GRBs are core collapse supernovae. So, at the end stage of its life, a star will collapse, and then it will actually undergo the supernova explosion. And as this is happening and it is exploding, it's able to launch a relativistic jet, which you can see here. So that is accelerating particles, again, to very high energies. And if that jet is pointed towards us, then we are able to see gamma rays and potentially neutrinos from particles in that jet crashing into nearby material or actually into each other. And that's the source of the gamma rays that we're seeing in the actual GRB. So this was an extremely bright burst. By some estimates, it's a 1 in 10,000 year burst. There's other estimates that say maybe it's 1 in a couple hundred years, but very, very rare. And it was so bright that both gamma ray instruments on the Fermi satellite were not able to keep up with how many photons they saw, so they both became saturated. So I'm going to show you an animation that shows you how bright the different GRBs have been over time. So these are previous record holders of the brightest GRB. So they're just getting brighter and brighter. This one was in 2019, about 80,000 counts at its maximum. This was the previous record holder prior to this burst. And this is this burst, but these instruments were saturated. So if you reconstruct how many photons actually were in the burst, it is orders of magnitude larger than any of the previous bursts and kind of blows all of the others out of the water. So this was an extremely bright gamma ray burst and a very exciting case for us to look at. So of course, on the IceCube side, we wanted to see if we saw any neutrinos from this burst. So we looked in IceCube data with 2 time windows. The first one was a total of 3 hours to cover the main part of the burst. So in real time, we got some public telegrams telling us when the burst happened, and we wanted to make sure that we covered the bulk of that emission for the burst. And then we also wanted to look out a little bit further and see if there was any later time emission. So maybe it took a little while for the neutrinos to be produced. So we looked in a time window of 2 days. And we actually didn't find any significant emission, so we were able to set upper limits. And what those limits are able to do is tell us some information about what's happening as the supernova is happening or slightly afterward. And so about 1 day after the detection of the boat, we sent our results. So actually it was about 26 hours, so pretty close to the end of this time window. And this is actually the header of the public telegram that I sent in real time for this follow-up. So we wanted to continue doing follow-up because the real-time limits only covered high energies, so TeV to PeV neutrinos, and we only looked in those 2 time windows. So we wanted to kind of expand that a little further. And so what we wanted to do is use the full energy capabilities of IceCube. So that stretches all the way from the MeV to the PeV in energy. So that's 9 orders of magnitude in energy. And then use a broad range of time windows. So the smallest was just the duration of that burst. And the longest was 15 days after. So that's actually 4 orders of magnitude in time. So this was a very large follow-up effort. And we actually, once again, did not find any significant emission, so we were able to set limits. So this is actually the paper that we published for that. And we were able to get stronger constraints on what's happening in GRBs on the neutrino side from this one burst than we have for the population of over 2,000 GRBs. So this is a very exciting GRB that we were looking at. So now I've talked a little bit about long GRBs, but now I'm going to kind of switch gears and talk about the other kind of GRB, so the short GRBs, which last less than 2 seconds, and they come from mergers of compact objects, so neutron stars and black holes. So here in this picture, it's 2 black holes that are orbiting each other and then eventually merging. So compact objects are some of the most extreme known objects. They are very, very dense. And when they orbit in a binary and eventually merge, they produce gravitational waves which have a characteristic signature. So here, I'm showing two neutron stars merging. I'm going to let it restart. So these are the two neutron stars merging, and you can see these waves kind of rippling out, and those are the gravitational waves. You see they increase in frequency as they get closer together until eventually they merge, and then they leave a black hole behind. So in light, they produce a short gamma ray burst as well as a kilonova. But they are also expected to produce neutrinos at the same time as the short GRB. So as they're merging, they're once again creating you can kind of see it in this animation, they're creating a relativistic jet that comes off of them, and that's where we're seeing the short GRB from, and then that's also where we would expect the neutrinos to be from. So how do we actually detect these mergers? Well, we detect these gravitational waves using ground-based detectors, which use what's called an interferometer. So this is a technique using lasers. So I'm going to show you an animation, which is actually from LIGO. So you can see the laser light coming into the splitter and going down the two arms, and then as a gravitational wave passes, the length of those arms actually changes slightly. So here, this is showing the laser light as it goes down one of the arms, and then is reflected at the end of that arm. And then they are recombined when they get together, and they are it's designed so that they completely destructively interfere when they're put back together. So essentially they cancel each other out completely. But then when a gravitational wave passes and it pulls one arm and shortens the other just slightly, then they would actually, you would see this interference pattern where they're no longer canceling each other out, and you're actually seeing the pattern that you expect. So we can see what we would expect in theory. So as the two objects, so in this case, I'm going to say they're black holes. So as these two black holes are orbiting each other, they have some frequency of their gravitational waves. And as they get closer together, the frequency of those waves actually increases until they actually merge. And you see this kind of peak, and then they very quickly damp down, and they kind of go to nothing. And so in 2015, the two ground-based gravitational wave detectors in the US, LIGO, the two LIGOs, actually saw the first detection of a binary black hole merger. So this is from 2015, and these on the top are actually their data. So you can see that characteristic signal that looks an awful lot like this one, which is with some extra noise. And then on the bottom, this is frequency versus time. So you can see the frequency actually increasing to produce kind of this chirp almost, and then kind of drops to nothing after they merge. So pointing back to a source is actually very difficult with gravitational wave detectors. You need multiple detectors so that you can use information from multiple of them in order to get any pointing. So with multiple detectors, you can use timing information, so who saw the event first, and some other information to reconstruct where the event actually came from. So here is a picture of one of the LIGO detectors. This one is in Louisiana. So this is LIGO Livingston. And then here is actually the global network of gravitational wave detectors. So we have LIGO Hanford, which is in Washington, LIGO Livingston in Louisiana, GEO, and then Virgo in Pisa, Italy, and then Kagra, which is in Japan. It actually has just been constructed, and then LIGO India is planned, but is not yet constructed. Is that another question? Oh, okay, sorry. So this is our global ground-based gravitational wave network, and by using data from multiple of these detectors, we are able to point back to where their source may have been. So that brings us to another multi-messenger success story, which is GW 170817. So on August 17th, 2017, the LIGO and Virgo detectors saw the merger of two neutron stars. So because they're neutron stars, it's a little fainter than the one that I showed you before, but you can still see, especially in Livingston, this little chirp here. So that's the actual merge. About 2 seconds later, a short gamma ray burst was observed by the Fermi Gamma Ray Burst Monitor. That's actually the same instrument that I talked about when I talked about the boat. And about 11 hours later, an optical counterpart was identified from the same source. So here you can see the different localizations as we're pinning down the source of those three things that were actually seen. And they were all associated with the same object, which is right here. So the gravitational waves, the short GRB, and the kilonova, which was the optical counterpart, was all identified from the same source. And so this was the first source that was seen in both gravitational waves and in light. Unfortunately, we did not see this one in neutrinos. So currently, the ground-based gravitational wave detectors are actually on again, and they're in their 4th observing run. So they've had 3 successful observing runs prior to this one. So that's 01, 02, and then 03 is the most recent, and then a little bit of a gap, which was kind of extended due to the pandemic, and then 04, which is where we currently are, and I put a line for now, so where we are now. We are actually in a bit of a break, so they did their first half, and then they are going to shut down and do some updates, so we're kind of in that shutdown period right now, and then they're going to turn back on in about a month, and resume observing for the rest of the run. For this, they actually have an improved sensitivity for, especially for the LIGO detectors. And currently, we're seeing about 1 merger every 3 days. They're mostly binary black hole mergers. And IceCube is following up every event that is detected by these gravitational wave observatories. And we're following them up in real time. I also didn't mention this, but I meant to. In 03, they started sending these out to the community as the event was happening, so in real time. So localizing a gravitational wave event is hard. We often get these localization areas that are hundreds or thousands of square degrees on the sky. So this is, again, a picture of the full sky. So once again, the whole globe, but looking outward. And this red area is showing you the probable region for where the source of the gravitational waves might have been. So it's a pretty large area on the sky. It's actually written on the side. It's about 1,000 square degrees for the 90% area. If we add neutrino information, neutrinos are about a few square degrees, so they're generally about 500 times better localized. So that's actually these blue events that you see here. So they're much better localized, and if we see a neutrino that's coming from, or that's coincident with this map, then we can send that out to the astrophysical community and say that there might be something here, and we can actually inform other astronomers that are trying to follow up these events, because often the field of view is not hundreds of square degrees, it's usually on the order of 10 square degrees maybe. So by doing this in real time, we're able to inform other observatories' follow-up efforts for these events. So what does this actually look like in real time? So what is my code actually doing? So a merger happens, and the ground-based gravitational wave detectors detect it. And in 30 seconds, they're able to send their first automated notice to the astrophysical community. And then my listener picks it up, and I get notified that me or someone else in my group gets notified that the ground-based gravitational wave detectors have detected an event. These can come at any time, so there have been several times in 04 that we've been woken up at 3 in the morning when the universe decides that there's going to be a merger of these objects. And then we start running the analysis. So we look in a period that ends up being about 15 minutes around the merger time. So we wait for that time window to close and to get all of our events, and then we start running the analysis. And that finishes in about 10 to 15 minutes, and then we send our automated notice out in about 10 to 15 minutes. So this whole process from when we get the notice to when we send our notice is about 20 minutes in total. So these are pretty fast follow-ups that we're actually able to send our results out to the community in a pretty fast fashion. So, like I said, the gravitational wave detectors are in the midst of their 4th observing run. And we have followed up every event that's been detected thus far, and we haven't found any significant emission yet. So these are the numbers thus far in 04. So these are how many candidates we have currently. So you can see 82 binary black hole candidates. Those are the majority of the mergers that we're seeing. 3 neutron star black hole candidates, and then actually no binary neutron star mergers yet. So we're hoping for at least one of those in 2024. The event that was the multi-messenger success story that I talked about was a merger of binary neutron stars, and that was the one that we saw the short GRB as well as the kilonova from. So that brings me to my summary. So neutrinos are an exciting window on our universe that allow us to understand processes happening near extreme astrophysical objects in a manner that's different than traditional astronomy. Searching for neutrinos in real time helps to inform other observatories' follow-ups of these objects, especially for localization for gravitational wave events. And there are more sources that I haven't been able to, or that I didn't have time to talk about, which is supernovae, active galactic nucleus flares, novae, and a couple others. So, yeah, thank you. And are there any questions?
Well, I guess we have a question from online from John Rummel. Please say a little more about yourself. When do you anticipate finishing your PhD, and what your job hopes are after that?
I feel like that's always a tricky question. I think likely for me, so 04 will actually run through around the end of this year, so I will definitely be around to finish that run. I think probably sometime in the year after that, I think would be kind of the goal. It might be a little longer than that, but that's kind of the goal. Yeah.
Very good. And Kevin has a question. Does the detection of a gravitational wave actually precede the ability to see the light from that merger?
That's a good question. I believe yes. Definitely for this one, definitely the answer is yes. For the one that I talked about, I believe the answer to that is yes. It generally we see the gravitational wave first. That travels at the speed of light, and we see that signature, and then the gamma rays that we're seeing are slightly after, only 1.7 seconds, so very slightly.
All right.
Yeah.
And myself, I was kind of wondering, with the vast outweighing of observations for merging black holes, does that say anything that maybe black holes are more common than we would expect? Like, it wasn't all that long ago we weren't even sure black holes even existed, and some astrophysicists were frustrated that a black hole seemed to be a solution to every vexing problem. But or does the frequency of those observations versus the ones involving the neutron stars, or maybe is it just because the neutron stars maybe are harder to detect because you don't get as big of a signal?
Yeah, I think that's more. It's tougher to see the signal from those, and then also because the signal from those is smaller, you actually can't see out as far either. So we can actually see much further out for these binary black hole mergers than we can for the binary neutron star mergers. So we actually are looking at a larger volume of space as well. I believe the rate of those is actually what was expected for this run. It's a little bit surprising that we haven't seen any binary neutron star mergers. So the rate for those was lower than, or the rate that we've currently seen for those is lower than expected.
Thank you. I guess Frank has another question.
Yeah.
Hi, I saw that you first saw the gravitational waves, and then, of course, the particles aren't necessarily traveling exactly at the speed of light, so they're shortly thereafter. But how does light get delayed by 1 hour? Because it's light. It should be getting there first, right?
Right.
So I can think of some reasons, but what do you think? I mean, what do you guys coming up with?
Yeah, that is a really good question that I think I will have to read a little bit more on. I think I need to read a little bit more on why the optical counterpart was so much later than some of the others. I think for the short GRB, it has to do with, I think, the formation of that jet and then the interactions of the particles before we actually get the gamma rays produced that we're seeing. So I think that is probably a little bit of the delay, but I think I need to read a little bit more on it.
I think there's also a modification in the general relativity, which for very high energy photons actually starts slowing them down. And the fact that they aren't seeing slower photons, what I was reading, means this can't really be happening, but maybe they are seeing slower photons. This is extraordinarily interesting. I mean, it's like 1 + 1, it doesn't equal 2. I mean, light has to travel. It wouldn't be scattering enough to be able to slow it down as it travels through space.
Right.
Because then it would be going some other direction.
Right, exactly, yeah. And it wouldn't, yeah. I think it's more about when it's produced and if it takes a little bit for these jets to actually be launched for the particles to interact with each other, I think is more what I'm thinking.
Okay.
But yeah, I'm not as familiar with the theory that you're talking about.
That's probably not what it is, but I thought that was just interesting.
Yeah.
Yeah, thanks, Frank. Does anyone else have a question for Jessie? Well, very great presentation, and it's great. Oh, we just love getting updates on what's happening at IceCube, and this is just like we were, the question Frank was posing. It must be fascinating to postulate, what processes are going on with these what are they called? They're not supernovas, but what was the term that for like the novas you get from two merging black holes or two merging neutron stars? It's not a supernova. It's what kind of nova was it?
The kilonova.
Kilonova. So yeah, that's fascinating to think about. What might be going on and learning more about through your observations. So I just wanted, on behalf of Madison Astronomical Society, we wanted to thank you for joining us this evening and giving this very excellent presentation. So I'd like to present you with this Madison Astronomical Society logoed coffee mug to enjoy a nice hot beverage when you're thinking about IceCube.
Thank you.
So I guess unless there's no other questions for Jessie tonight, we'll be having our next meeting on Friday, March the 8th, I believe. And we will be talking about the total solar eclipse coming up in April. So it's great seeing everyone, and we'll see you next month. And that's the conclusion of tonight's meeting. Have a good month, everyone.